Hello viewers, in today's session we are going to discuss an important and conceptual problem from differentiability of functions. And here we are going to discuss this problem where we have to prove that the function f of x, that is mod of x square minus 1, is not differentiable at x is equal to plus minus 1, right? So we have already discussed an important problem regarding this function in our earlier video, but here we are going to prove the non-differentiability of this function at these two points, right? So the domain of this function f of x is the set of all real numbers, right? And this function is differentiable everywhere, that is for all values of x belonging to R except these 2 points, that is x is equal to plus 1 and x is equal to minus 1. So let us see how we can prove that this function is not differentiable at these 2 points using the concept of right hand derivative and left hand derivative. But before applying the concept of right hand derivative and left hand derivative, it is important to redefine this function f of x in terms of intervals, right? So let us first define this function using the fundamental definition of mod function. So now the definition of mod function goes like this. Mod of p is a positive p whenever p is greater than 0. Mod of p is 0 whenever p is 0. And mod of p is negative p when p is less than 0. So here we have mod of x square minus 1. So let us replace this p with x square minus 1. So we can define f of x, that is mod of x square minus 1, like this, that is positive x square minus 1 when x square minus 1 is greater than 0, and mod of x square minus 1 is equal to 0 when x square minus 1 is equal to 0. And here mod of x square minus 1 is equal to negative of x square minus 1, that is 1 minus x square when x square minus 1 is less than 0, right? So now we have to solve these two inequalities and this quadratic equation. So from here we can now write x square is equal to 1, and this implies x is equal to plus minus 1, right? So here we have to prove the non-differentiability of this function at these 2 points, right? So let us now solve these two inequalities. So here the first one is x square minus 1 is greater than 0, that is x square is greater than 1. So we can also write x square greater than 1 square. Now this inequality is of this form, that is x square is greater than say a square, right, where a is equal to 1. So the solution of these type of inequalities is given by x belonging to the interval minus infinity to minus a union a to infinity, right? So here we are using the direct result. So the solution of this inequality is given by x belonging to minus infinity to minus 1 union 1 to infinity, right? And the solution of this inequality can be written like this: x square minus 1 is less than 0, so x square is less than 1, taking minus 1 to this side, and here we can write it as 1 square. This is of this form: x square is less than a square. Now again a is equal to 1, and the solution of these kind of inequalities is given by x belonging to minus a to a, right? So here we have x belonging to minus 1 to 1, right? So these are the solution of these two inequalities. So now here we can write x belonging to minus infinity to minus 1, union 1 to infinity, and here we can write x belonging to minus 1 to 1, right? So let us draw the real number line. Here we have minus infinity, here we have plus infinity, and the 2 points are minus 1 and plus 1, and at these 2 points the function is not differentiable, right? So when we take this interval minus infinity to minus 1, then the form of the function f of x is given by here x square minus 1, and when we take this interval that is from 1 to infinity, then the function f of x is defined like this, that is x square minus 1, and when we take x belonging to minus 1 to 1, then the function f of x takes this form, that is 1 minus x square, right? So this is the complete description of this function f of x. So now we are in a position to find out the right hand derivative and the left hand derivative at these 2 points, that is x is equal to 1 and minus 1, right? And from the definition of differentiability of a function, we know that if the right hand derivative and left hand derivative both exist and they are finite and they are equal to each other, then the function is said to be differentiable. But if the right hand derivative or the left hand derivative doesn't exist or they are not finite, then the function is not differentiable. Or in other case, if the right hand derivative and left hand derivative both exist, they are finite but they are not equal to each other, then also the function is said to be non-differentiable, right? So let us first take this point x is equal to plus 1, and let us first find out the right hand derivative and the left hand derivative. So now the right hand derivative is defined by this limit, that is right hand derivative is given as here we can write f prime, and here we can write a. A is the point where the right hand derivative is to be determined, and here we put a positive sign. So this is the notation for right hand derivative, and it is given by limit h tends to 0, and here we have f of a plus h minus f of a divided by h, and the left hand derivative is defined like this, that is f prime of a, and here we put a negative sign, and the limit is given as limit h tends to 0, and here we have f of a minus h minus f of a divided by minus h. So this is the definition of right hand derivative, and the left hand derivative at some point, say x is equal to a, and remember the point should belong to the domain of the function, right? And here both the points x is equal to 1 and minus 1, they belong to the domain of this function f of x. So now consider this point x is equal to plus 1. So the right hand derivative is given by f prime, and here we have one positive, and this is given by limit h tends to 0, f of 1 plus h minus f of 1 divided by h. So this is limit h tends to 0, and here we have f of 1 plus h. Now see, h is infinitesimally very small. right? And it is a positive quantity. So 1 plus h, it belongs to this interval, that is 1 to infinity, because h is infinitesimally very small, but it is a positive quantity. So 1 plus h is always going to be greater than 1, right? So 1 plus h belongs to this interval, that is 1 to infinity, that is 1 plus h, it lies somewhere between 1 and infinity, right? So when 1 plus h belongs to this interval 1 to infinity, then the form of the function is x square minus 1. So here f of 1 plus h can be obtained by substituting x is equal to 1 plus h in this expression. So here we have 1 plus h square minus 1 and f of 1. Now f of 1 is obviously 0, because f of x is 0 when x is equal to 1. So f of 1 is 0. So here we have 0, here we have h. Now this is limit h tends to 0, and we can expand 1 plus h whole square by using the standard identity, that is a plus b whole square. So we have 1 plus h square plus 2h minus 1, and then we have h. So 1 and minus 1 get cancelled. We have limit h tends to 0, h square plus 2h over h, and here we can take h common. So we have h plus 2 divided by h. So h and h get cancelled. So we have limit h tends to 0, and here we have simply h plus 2. Taking h is equal to 0, we have 0 plus 2, that is equal to 2. So the right hand derivative of this function at x is equal to 1 is given by 2. So here we can write f prime of 1 positive is equal to 2. So now let us find out the left hand derivative. So now the left hand derivative is given by f prime. Here we have 1 minus, and we have limit h tends to 0, and here we have f of 1 minus h minus f of 1 divided by minus h. So now here we have 1 minus h. Now again h is infinitesimally very small, and h is a positive quantity, so 1 minus h is less than 0, right? So 1 minus h less than 0, so it means 1 minus h should lie between minus 1 and 1. So 1 minus h, it lies somewhere over here, right? Because it is very close to plus 1, but it lies towards the left of x is equal to 1. So when we have 1 minus h, x is equal to 1 minus h, then the form of the function is 1 minus x square, right? Because when x belongs to this interval minus 1 to 1, then f of x takes this form 1 minus x square. So here we have limit h tends to 0, f of 1 minus h can be obtained by replacing x by 1 minus h. So we have 1 minus h square, and here f of 1 is 0. So here we have minus h. So let us simplify it. So we have 1 minus 2h plus h square, and here we have minus h. So we have limit h tends to 0, 1 minus 1 plus 2h minus h square over minus h. So these two 1 and minus 1 get cancelled, and we have limit h tends to 0, 2h minus h square over minus h, right? So we have limit h tends to 0, we can take here minus h common. So we have now here minus 2, and here we can write plus h, right? And here we have minus h. So taking minus h common in the numerator, right? So we have now minus h and minus h get cancelled. So we have limit h tends to 0, and we have minus 2 plus h, right? So taking h is equal to 0, we have minus 2 plus 0, that is minus 2, right? So the left hand derivative of this function f of x is now given by minus 2. So here we write the left hand derivative at x is equal to 1 as minus 2. So now we can conclude that although the right hand derivative and the left hand derivative both exist and they are finite, right, but they are not equal to each other. That is 2 is not equal to minus 2. So the right hand derivative is not equal to the left hand derivative, or we can write here f prime of 1 plus is not equal to f prime of 1 minus, right? So here the right hand derivative and the left hand derivative are not equal to each other. Therefore we can conclude that this function is not differentiable at x is equal to 1, right? So similarly we can prove that this function f of x is not differentiable at x is equal to minus 1. So now let us consider the second point, that is x is equal to minus 1. So now the value of a is equal to minus 1. So the right hand derivative can now be written as f prime of minus 1, and here we put a positive sign, and here we have the limit h tends to 0, f of minus 1 plus h, and here we have f of minus 1, and here we have h, right? Now the value of f of minus 1 is also equal to 0, because f of x is equal to 0 when x is equal to minus 1, and we can also calculate the value of f of minus 1 and f of 1 by directly substituting x is equal to 1 and minus 1. That is 1 square is 1, so 1 minus 1 is 0, minus 1 square is 1, 1 minus 1 is 0, right? Okay, so now let us find out the value of this limit. Now see, here we have minus 1 plus h, that is minus 1 plus h, which can also be written as h minus 1. Now h is infinitesimally very small, but it is a positive quantity. So h minus 1 is less than 0 and greater than a minus 1, right? Now see, h is greater than 0 but less than 1. So now if we subtract 1 throughout this inequality, then we can have here a 0 minus 1, here we have h minus 1, and here we have 1 minus 1. So this is minus 1, this is h minus 1, this is 0. So h minus 1 is greater than minus 1, but it is less than 0, right? So here we have 0 somewhere between minus 1 and 1, right? So h minus 1, it lies within this interval, that is from minus 1 to 1, and the form of the function f of x is 1 minus x square, right? So to get the value of f of minus 1 plus h, we have to substitute x is equal to minus 1 plus h in this expression, right? So we have here 1 minus minus 1 plus h square, and f of minus 1 is 0, and here we have h, right? So let us simplify it. So we have limit h tends to 0. This is 1 minus, and here we have 1 plus h square minus 2h, and here we have h. So this is limit h tends to 0 and 1 minus h square plus 2h over h, and 1 and 1 get cancelled, and we have limit h tends to 0 minus h square plus 2h over h. Taking h common in the numerator, we have h minus h, and here we have 2 and h and h get cancelled, so we have limit h tends to 0 minus h plus 2. So now we can take h is equal to 0. So we have minus 0 plus 2, that is 2, right? So the right hand derivative of this function at this point, x is equal to minus 1 or a is equal to minus 1, is given by 2. So now let us find out the left hand derivative. So the left hand derivative is given by this limit, that is here we have minus 1 and minus, and here we can write limit h tends to 0 f of minus 1 minus h, and here we have f of minus 1 divided by minus h, right? Now see, here we have minus 1 and minus 1 and minus h, right? Now this expression can also be written as minus 1 plus h, right? So here we have a negative sign, so it implies that minus 1 plus h, it lies between minus infinity and minus 1, because see, h is greater than 0 but less than 1. So if we multiply throughout by negative 1, then we have 0, then we have minus h, and we have minus 1. The direction of the inequality get reversed, and here if we add minus 1 throughout, then we have a 0 minus 1, then we have minus 1 minus h, and here we have minus 1 minus 1. So we have minus 1 minus h, and this is minus 2. So we have minus 1 minus h is greater than minus 2 but less than minus 1. So minus 1 minus h, it lies in this interval, that is minus infinity to minus 1, right? So when minus 1 minus h lies in this interval minus infinity to minus 1, the form of the function f of x is given by x square minus 1. So here we'll substitute x is equal to minus 1 minus h. So now we have here limit h tends to 0, and f of minus 1 minus h is given by minus 1 minus h square and minus 1, and f of minus 1 is 0, and here we have minus h, right? So let us simplify, and here we have simply 1 plus h square plus 2h, and here we have minus 1, and here we have minus h. So this is limit h tends to 0, and 1 this 1 and minus 1 get cancelled, and we have h square plus 2h over minus h, and we have limit h tends to 0. Here we can take h common, so we have h plus 2 and divided by minus h. Now h and h get cancelled, so we have minus this negative sign, limit h tends to 0, and we have h plus 2. So now taking h is equal to 0, we have minus 0 plus 2, that is equal to minus 2. So now the left hand derivative of this function at x is equal to minus 1, is given by minus 2, right? So we have now seen that the right hand derivative of this function at x is equal to minus 1 is given by 2, and the left hand derivative is given by minus 2. And here we can see that the right hand derivative and the left hand derivative both exist and they are finite, right? But they are not equal to each other. That is 2 is not equal to minus 2, that is the right hand derivative is not equal to the left hand derivative. Therefore we can claim that this function f of x is not differentiable at x is equal to minus 1, right? So viewers, this is how with the help of the concept of right hand derivative and the left hand derivative, we can easily prove the differentiability or the non-differentiability of a function at a given point in its domain.